Chapter 26, Stereoisomerism. Stereoisomers are mirror images of each other. So let's review isomers. We have molecules that are the same chemical formula, but they're different in A, either how the atoms are connected, which is a structural isomer, or how the atoms are arranged in space, which is a stereoisomer. So here we see structural isomers of butane. So you have butane and isobutane. And they both have 4 carbons and 10 hydrogens. So they're both C4H10, but the actual atoms are connected in a different way. Whereas in butane you have 4 carbons connected in a row, and isobutane you have 3 carbons and 1 branching off. That makes them a structural isomer. The actual atoms are connected in a different order in the 2 cases. Or ethanol and methoxymethane, dimethyl ether. Again, here we have C2OH6 or C2H6O. Both of them have 2 carbons, 6 hydrogens, and 1 oxygen. The only difference is how those atoms are connected to each other in space. And that makes them a structural isomer. 1-chloropropane or 2-chloropropane. Both have 3 carbons, both have 7 hydrogens, 1 chlorine, but is it coming off of a terminal carbon or the middle carbon? Again, same exact atoms, but connected in a different order. Stereoisomers are compounds that have the same structural formulas, but are different in their spatial arrangement. And so there's 2 types, the cis-trans isomers, and then, like I said earlier, the optical isomers, which are mirror images of each other, like your left hand and your right hand. If you look at your hands are mirror images of each other. There's no way I can maneuver my right hand so it exactly fits over my left hand. Because if I try to put my right over my left, I see my thumbs at the other side. And so optical isomers are mirror images of each other. So again, we have cis-trans or geometric isomers, and then optical isomers. And in this way, the same atoms are connected to the same atoms in the same order, but in a different spatial way. Like in both cis and trans 2-butene, you have 4 carbons connected in a row, and you have a double bond between carbons 2 and 3. The difference is cis and trans, the spatial arrangement of the bond, because there is no rotation across a double bond. Optical isomers. Optical isomers are named optical because they have the ability to rotate the plane of polarized light. So if you shoot light through a sample that has an optical isomer, it'll rotate that light. And how much that light is rotated is measured when we try to work out how much chemical is there. So again, plane polarized light is light that is vibrating in only one plane. So here you see ordinary light, which has light moving in all our light frequencies and wavelengths in all directions. And here's polarized light, just one plane. And so we can pass ordinary light through a polarizer to produce polarized light. And now, and that's what's happening here, you pass normal light through a polarizer, and now I have plain polarized light. It's just going up and down. I see how it gets twisted as it goes through my optically active sample. And we can measure how much that rotation, the angle, gets moved. And that is an optically active compound. If there's no rotation, then it's not optically active. And that's usually the case in chemistry, because generally when you make a chemical, even if there are mirror images, you'll make both of them in 50-50%. It's actually quite difficult to purposely only make one mirror image and not the other. Most often you actually have to use biological molecules like enzymes to produce something like this, because enzymes, biological molecules, are optically specific. For example, humans only make L-alanine. We don't make D-alanine like bacteria do. And so using enzymes, you can specifically produce optically active compounds. But doing so chemically, now we're talking about needing chiral catalysts, and that is a lot more difficult. And that's outside the scope of this class. That would be for much more advanced organic chemistry classes. So optical activity is the ability of a chemical substance to rotate plane polarized light to the right or to the left. If it rotates light to the right, it gets named dextrorotary, and it's D. If it rotates light to the left, it's levorotary, and that's L. And again, D is also positive, dextrorotary is also positive, levorotary is also negative. Chirality. Chirality is a necessary condition for optical activity, and it is a property present in an object that cannot be superimposed on its mirror images, like your right hand and your left hand are chiral. Chiral objects do not have a plane of symmetry. They are asymmetric. Superimposable means that when we lay one object on top of another one, they can coincide exactly. So, your right and your left hand are mirror images of each other. They are not superimposable. There's no way you can rotate your right hand so that it's exactly in the same position as your left hand. And therefore, they're chiral objects. To have a chiral carbon, we need 4 different things coming off the carbon. If two of those are the same thing, you'll have a line of symmetry. So if A and B are the same thing, all of a sudden we have a line of symmetry through the molecule, and it is no longer chiral. So carbons are only chiral if they have 4 different substituents coming off of them. And chiral molecules, they are not superimposable on their mirror images. Achiral molecules are superimposable. So for example, number 3 here. If we take its mirror image, and you just rotate it 180 degrees that way, you have this molecule again. It is not chiral because you have 2 hydrogens. To have a chiral carbon, you have to have 4 different groups coming off of that center carbon, like with alanine. And here we see our mirror plane, and we have S-alanine and R-alanine. And we'll get to the rules on S and R in a little bit here. So draw the mirror image isomers for the following compounds that can exist as stereoisomers. Well, we have to look through our carbons and find a carbon that has 4 different things attached to it. So here, this carbon has a methyl group, a hydrogen, an OH, and then an ethyl hydroxy group coming off of it. So this is the only chiral carbon here. And so when we draw it, we draw our molecule, we put a mirror plane, and now we draw the mirror image, what it would look like in the mirror. Here, this carbon is our chiral carbon. It has 4 different things attached to it. A methyl group, a hydrogen, a bromine, and then an isobutyl group. And here we see the mirror image. Draw all the structural formulas for the butyl alcohols and indicate which molecules have optical activity. Well, here there are 4 structural isomers, because the 4 carbons can either be in a straight chain or they can be 3 with 1 branching off of it. If they're in a straight chain, the OH group can either be on one of the terminal carbons, both are really the same spot, or they can be in one of the middle carbons. So you either have 1 butanol or 2 butanol. Placing it here would just still give us 2 butanol. We just start counting from the other side. And here we have methylpropanol. And the OH can either be on a terminal, this one, and this one. Those 3 methyl groups are the same. So it could be there, or it can be on the middle carbon. And so in this way we have 2-methyl 2-propanol, or 2-methyl 1-propanol. So we have 4 structural isomers. Which one of these will have optical activity? Well, let's look at our first one. This carbon does not have 4 things. This one does not have 4 unique things. Neither does this one. Neither does this one. 1-butanol, not chiral. Here, this carbon has 3 hydrogens, doesn't count. This carbon has 3 hydrogens. This carbon has 2 hydrogens. This carbon has 2 methyl groups on it. So that methyl group is exactly the same as that methyl group. So that carbon's not chiral either. And so this molecule is not chiral. Here, these 3 carbons all have 3 hydrogens on them. They do not have 4 separate groups on them. They're all 3 hydrogens and something else. And this middle carbon has an OH, but then it has 3 methyl groups. And so it does not have 4 unique chemical groups on it. And so it's not chiral. Only here in 2-butanol do I finally find a carbon that has 4 different groups on it. An OH group, a methyl group, a hydrogen, and an ethyl group. All 4 are different from each other, and therefore I finally have a chiral carbon, and I finally have an optically active molecule. Fischer projection formula. This is a 2-dimensional structural formula used to represent 3-dimensional structures on paper. And that's a tough thing to do, to try and accurately show 3-dimensionality when you're writing on 2-dimensional paper. And so this is just one of the tricks chemists use. When they draw in Fischer projections, any bond going left or right is actually coming forward. It's coming out of the paper. So that OH is actually up here. The H is here. So the lateral bonds are coming towards you. The vertical bonds are going into behind the computer. And so that's how we view a Fischer projection. Horizontal bonds represent bonds that are coming forward. They're in front of the plane of the screen. The vertical bonds are going behind the plane of the screen, giving you a 3-dimensionality. So you can't turn formulas 90 degrees because that changes whether the bonds are coming towards you or away from you. Fischer projections are useful with carbohydrates. You'll see them a lot next chapter with carbohydrates. But again, this is 3 different ways to draw the exact same molecule. Again, these solid wedges means the bonds coming towards you. The dashed wedges means those are going away. They're behind the screen. And then here we see our Fischer projection. So our molecules A and B, the same molecule. Let's rotate it. So it looks, let's say, we rotate it. And notice the big difference is this OH will go here, just like here. This hydrogen will go here, but now the COOH group will be down here. But does that actually change the orientation? And it does. So they are not the same molecule. They're not superimposable. There's no way to rotate these 2 molecules to make them fit on top of each other. Because if we flip it, now the carbons and the COOH groups will be on top of each other, but the OH group will be over here and the H group will be over there. And if we flip it back, the OHs and the H are superimposable, but the other 2 groups aren't. And so there's no way to make this fit on top of the other molecule. Thus, they are indeed mirror images of each other, and they are chiral. And that's what you would have expected, because look at your carbon. You have a hydrogen, a hydroxy, a methyl, and a carboxylic acid group. All 4 groups coming off the central carbon are different from each other, letting you know that that is a chiral carbon, so the mirror images should not be superimposable. They will be stereoisomers, and they will be optically active. So redraw the Fischer projection as a 3-dimensional formula. Again, the horizontal bonds come towards you, forward from the screen as the solid wedges, and the vertical bonds go backwards behind the screen as dashed wedges. Enantiomers. These are optically active. They are non-superimposable mirror images. They are chiral. So we call these types of mirror images enantiomers. Positive enantiomers rotate light to the right. Negative enantiomers rotate light to the left. And they have identical physical properties except for the specific rotation of light. That's actually not true. There was a horrible case with the drug thalidomide, in which one of the optical isomers was a great morning sickness drug, and the other optical isomer caused terrible birth defects. And so in biochemistry, especially in a biological system, the optical isomer matters, and different optical isomers can have different biochemistry. In normal organic chemistry, they typically have the same physical properties, but in their biochemical properties, as it says here, they can be very, very different from each other, dangerously so.